So we're going to start with example 2 on your paper. We want to decide whether this series, which is written in summation notation, converges. So probably you'll get used to reading summation notation. If at the beginning you're not sure, you might like to write out the first several terms of this series to decide, so you can tell whether it's geometric or something else that we recognize. So this notation means I'm going to start by letting n equal 1. So if I look at the series inside the summation symbol and I replace the n with 1, I'm going to have 3 times 1/2 to the 0. 1/2 to the 0 is 1, and 3 times 1 is just going to be 3. I'm going to add to it what happens when I let n equal 2. So n equals 2, I'm going to have 3 times 1/2 to the 2 minus 1 is 1. The next term is going to be 3 times 1/2 to the 3 minus 1, so 1/2 squared, plus 3 times 1/2 to the 3rd, plus ... So what we want to do here, especially now at the beginning, our only tool in our tool belt really is if we can decide if a series is geometric or not. But it does seem that in this case, the series is geometric. The number I'm multiplying by every time, so in this case my r equals 1/2, and a, which stands for the first term, I can tell is 3. So this sequence is geometric, so it will converge as long as r is in between -1 and 1, which it is. 1/2 is between -1 and 1, and it will converge to a value of a over 1 minus r. So in this case, 3 over 1 minus 1/2. I can simplify that. That's 3 divided by 1/2, which is 3. Oh, no, it's not. 3 divided by 1/2. Yeah, marker. 3 divided by 1/2, which is the same as 3 times 1/2, which is 6. For the next example, they wrote out the sequence for me. It's 1 minus 1/2 plus 1/4 minus 1/8 plus ... What they've written here at the end of this problem is what's known as the general term. It's a term that has a variable n in it, and you could plug in any value n to figure out what the nth term is. All right, so here I have, do I have a geometric sequence? Yeah, it looks like every time to get from one term to the next term, I multiply by -1/2. So in this case, r equals -1/2. A is the first term, which is 1. So this series is geometric. R is in between -1 and +1. So this series will converge, and it will converge to a sum of 1, which is a, over 1 minus -1/2. So in this case, it's going to be 1 over 1 minus -1/2 is the same as 3/2, and 1 over 3/2 is 2/3. So part C, I have the infinite series, which is the sum as k goes from 0 to infinity, of 3/5 raised to the k power. I'm supposed to decide if this series converges or diverges, and if it converges, I'm supposed to find the sum. So again, you might be able to recognize without writing this out a little bit later, but right now if you want to write it out, this means I'm going to let k equal 0. So I'll have 3/5 to the 0, which is 1, plus the term I get when k equals 1, which is 3/5 to the 1, plus what I get when k equals 2, which is 3/5 squared. And I think I can see the pattern now. To get from one term to the next, I'm always multiplying by the same value, which is r, and that's 3/5. A in this case is 1. This is a geometric series, and r is in between -1 and +1. So this series does converge, and it converges with a sum of 1, which is a, over 1 minus 3/5. So 1 minus r. That's 1 over 2/5, which is 5/2. Okay, for this last one, part D, I have a series here, and I'm supposed to decide if it converges. So first I'm going to check to see if it's a geometric series. Is there something that I multiply by every time to get the next term? So notice you could always check this by taking one term, like the second term, and dividing it by the term in front. Then taking this term and dividing by the term in front of it. If you always get the same ratio, the same quotient, then that is equal to r. Maybe also you could tell just by looking. So I can tell here that I'm always multiplying by pi over 2. So this is in fact a geometric series, and r is pi over 2. A happens to also be pi over 2. A is pi over 2 because the first term is pi over 2. R is pi over 2 because that's the value I multiply it by every time to get the next term in the series. So the question here is, does this series converge? And my answer is no, this series would diverge because it is a geometric series. R is pi over 2, and pi over 2 is not in between -1 and 1. I would say this series diverges because r, which is pi over 2, that's an equal sign, is bigger than 1. All right, so a couple of definitions here we'll squeeze into this video. A power series is a series, so the sum of a bunch of expressions, a bunch of the terms in a sequence, right? And in a power series, there are coefficients, so here they happen to be called C0, C1, C2, Cn, so C for coefficient, and every coefficient is multiplied by a power of x, and those powers of x increase by 1 every time. So a power series, a coefficient times a power of x. That's a power series that is centered at x equals 0, and we'll talk more about what that means to be centered at x equals 0. There's a sort of a fancier version of a power series in which we still have a coefficient multiplying every term, but the second part, the second factor in every term, is a power of not just x, but of a tiny binomial x minus something. And in this case, so if we call it a, if that x minus a is our tiny binomial, then a is the center of the series. So we are going to talk about what would it look like to graph a power series. If you graphed a power series that's centered at 0, the center is 0. And if you graph a power series that's centered at some value a, then the whole picture just shifts over to a. So this x minus a performs a horizontal shift, a spaces to the right.